Assalamu alaikum. Welcome back to the lecture series for operating systems. I hope you're doing well. Let's start lecture 3. We are continuing the chapter called processes. In the last lecture, we talked about process states. In this lecture, we are going to continue from the previous topic. Please refer to the third chapter of the William Stallings book for this topic. Let us first review the things that we learned in the last lecture. We introduced the concept of a process, and I told you that a process is a program in execution. We saw the reasons due to which a new process is created and the reasons which can lead to its termination. We introduced the concept of virtual memory and process suspension. We traced the life of a process from birth to death and explored the different states that it can have in an operating system. Now let us talk about the data structures that an operating system maintains for the processes that it manages. Our subtopic for this lecture is process description. Let us start with an example multi-programmed environment. There are n processes in a virtual memory system. Shared system resources include the processor, I/O devices, and main memory. Take a moment to guess which process is running, which process is suspended. So, do you have the answers? To find out who is running, see which process currently possesses the processor. You can see a solid arrow going from P1 to the processor. So this means that P1 is running. To find the suspended process, find the one who is not mapped to main memory. You can see solid arrows going from P1 and P2 to main memory, but there is a dashed arrow from Pn to main memory. So what this signifies is that Pn is only loaded in the hard disk area of virtual memory. Not even a single page of Pn is in the main memory. So this means that Pn is suspended. Let me elaborate more. P1 is currently running and is loaded in the main memory, at least partially. It has access to two I/O devices. P2 is also at least partially loaded in the main memory and has access to the third I/O device. But when it asked for one of the I/O devices that P1 has, it was blocked. When P1 relinquishes the leftmost I/O device, P2 will be given the device and unblocked. The role of operating system in a multi-programmed system is manifolds. It has to create and manage processes, schedule and dispatch processes to the processor, allocate and deallocate virtual and primary memory spaces to processes, allocate I/O resources to processes, and respond to operating system service calls by processes. If you remember, an operating system service call is a call made by a process requesting a service from the operating system. The data structures that the OS uses to keep track of the system are shown here. Most OS have memory tables for memory management, I/O tables for device management, file tables for file management, and process tables for process management. We will talk about these tables one by one. These tables are cross-linked so that we can find which memory is allocated to which process, what I/O devices have been granted to it, which files it has access to, etc. These tables are usually maintained in the main memory, as the OS has to refer to them frequently. Memory tables are used to keep track of both primary and secondary storage. A part of main memory is reserved for the operating system, the system address space. The rest of main memory is used by the processes and it is called the user address space. All processes are completely loaded in the hard disk portion of virtual memory. Memory tables must include these pieces of information. Allocation of main memory to processes, how address spaces have been allocated to the processes in main memory. Allocation of secondary memory to processes, where do the processes reside on secondary storage. Protection attributes of blocks of main or virtual memory, such as which processes may access shared memory regions. Protection attributes means rights and permissions, like which process has the right to read or write a block of memory, or which processes are sharing memory blocks and what memory blocks they are sharing. Any information needed to manage virtual memory. This includes information like page size. Recall that processes are divided into chunks called pages. Your computer architecture teacher will tell you about virtual memory in detail. I/O tables are used to manage I/O devices. I/O tables must include these pieces of information. Availability or assignment of I/O devices. An I/O device may be free or assigned to a process. And if it is assigned to a process, we need to know which process it is. Status of an I/O operation in progress. The OS needs to know if an I/O operation has started, if it is successful or unsuccessful, if there is an error, and what error it is. Location of main memory used as source or destination of an I/O transfer. If we are performing input, there will be a memory location that will serve as destination and will receive data coming from the device. If we are performing output, there will be a memory location that will serve as source and will provide data to be sent out. File tables are used to manage files in main and secondary storage. File tables must include these pieces of information. Existence of files. A user may ask for a file which does not exist, and the OS must inform the user adequately. Location of files on secondary storage. The OS must know the exact platter, sector, and track on the hard disk assembly which contains the block of a desired file. The OS must know the number of blocks of each file, their sizes, and their locations. Otherwise, file retrieval would be impossible. Status of files. A file may be already opened by another process. A file may be in the process of being written on by a process, so it can have different statuses. File attributes. A file can be read-only or writable. A file can be private or shared among users or processes. In some operating systems, there is a separate file management system, so the OS does not bother about files. Process tables are used to manage processes that exist in the system. The topic of process description deals with process tables and data structures that help the OS to manage processes. So the rest of our discussion will be relevant to process tables. These tables must include the following information. Location of processes. The OS needs to know where a process is on secondary storage and in main memory. Attributes of processes. The OS needs to know the parent of the process, the ID of the process, the state of the process, etc. Let us start with this question. What is the physical manifestation of a process? In simpler words, if a process is sitting in front of me, what will it look like? So what I'm trying to do is to create a picture of a process in your mind so that you are able to identify a process when you see it. The process image is a collection of things that are kept in the address space that the operating system assigns when it creates a process. There are four things that are kept in the process's address space, or there are four components of the process image. User program, that is the program that you want to execute. User data, values that the user has provided as individual variables or in complex data structures like arrays, matrices, linked list, trees, etc. Stack, this is to handle procedure and system calls. In data structures, you must have read that stacks are used to handle function calls. When a function is called, we push our variables and the address of the current line of code onto a stack. Then we jump to the body of the called function. When we finish execution of the called function, we pop from the stack. In this way, we retrieve the address of the line of code to which we must return and the values of variables that existed in the calling function. Transfer of control from one function to another cannot take place without stacks. That is why each process has a stack in its image. And the fourth part is process control block, the process's ID card. If the process is suspended, all pages of the process image are on the hard disk. Otherwise, at least one page of the process image is loaded in the main memory. The OS needs to know the locations of all pages of the process image to be able to fetch and execute the process. This information is maintained by the memory management part of the operating system, which keeps the memory tables. Last night, I asked my friend Process A to send me a selfie via WhatsApp, and this is his reply. Doesn't he look amazing? Going back to operating system control structures, let us concentrate on processes only. There is a primary process table with one entry for each process. Each entry contains a pointer to the process image. If the process image spans multiple blocks, the entry in the primary process table may have a pointer for each block. or it may simply cross-reference to the memory table entry for this process. So this concludes our discussion about process location. Let us talk about process attributes. The OS generates a process control block or PCB for each process that it creates. This data structure has a lot of subfields. We can characterize information contained in a PCB in three broad categories: process identification, processor state information, and process control information. Process identification. This section of the PCB stores various identifiers relevant to the process. Notable values include process ID, identifier of this process; user ID, identifier of the user who created this process; parent ID, identifier of the parent process. Processor state information. This section contains contents of the processor's registers. This is the context of the process, which is saved when it is preempted from the processor and restored when the processor is allocated to it. For any processor, the register set includes user visible registers, registers of the processor that can be altered by machine instructions executed in user mode of the processor are called user visible. Control and status registers, registers employed to control the operation of the processor. We will explore these shortly. Stack pointers. Remember there was a stack in every process image? A stack pointer points to the top of a stack. Let us elaborate control and status registers. Program counter is the register that drives the processor. It tells the processor which instruction to execute. Condition codes like sign, zero, carry, equal, overflow give information about the result of the most recent arithmetic or logic operation. Status information refers to the value of the interrupt flag, which would determine if interrupts are enabled or disabled during execution, and the value of the execution mode bits, which would determine if the processor is in kernel mode or user mode right now. All processors contain a register or a set of registers called the program status word or PSW for short, containing status information. Condition codes are a part of the PSW. In Intel x86 processors, the PSW is the E flags register, shown here with all its bit positions labeled for you. This picture is from your book. You can always move back to this slide because there are a few things that I want you to answer relevant to this slide. Now students, open a Word file, save it as my roll number underscore lecture underscore 3, pause the video and try to write the answers to these tasks. Task number 1. In the E flags register, identify the bits relevant to interrupts and execution mode. Task number 2. In the E flags register, identify the bits relevant to condition codes. You may use the book I have already shared its link in Google Classroom. A few more questions for you. Can you define parity? Can you define overflow? Process control information. This section of the PCB contains information used to coordinate and control various active processes in the system. It includes the following information: scheduling and state information, data structuring, inter-process communication, process privileges, memory management, resource ownership and utilization. Now I will talk about each one of these. Scheduling and state information. This information is needed to properly schedule the process. This section includes information like process state, new, ready, running, blocked, the states we saw in the 7-state process model in the previous lecture. Priority. If the system enforces priorities, we need to know the priority level of each process. Event. The ID of the IO event the process is waiting for if the process is blocked. Scheduling related information like execution time of the process in its last run, waiting time of the process. Why do we need scheduling related information? Consider a scheduling algorithm which selects the process with the smallest running time to be dispatched to the processor. For this algo to execute, we will need the last running times of all the processes in the queue. Only then we will be able to pick the process with the shortest running time. Then there is another scheduling algorithm which selects the process who has waited the longest to be dispatched to the processor. For this algo to execute, we will need the waiting times of all processes in the queue. Only then we will be able to pick the process with the longest wait. Data structuring. A process may be linked to other processes in a queue, a ring, a tree, etc. This section contains pointers to other processes to support these structures. Remember the linked list? Every node contains a pointer to the next node. If I create a queue of processes using a linked list, then every node is a process and every process must carry a pointer to the next process. So this part of the PCB contains that pointer to the next node. Also, if B is the child of A and they form a tree, then A must have a pointer to its child B. So this section of the PCB will keep the child pointer. Inter-process communication. Communication between processes in a system is called inter-process communication. When a system has many processes, we can have a scenario where one process generates data and another process or a set of processes use it. If this happens, the generating process will have to send data to the using processes. This will lead to data transfer or communication between processes in the same system. Inter-process communication uses flags, variables, or messages, and we will cover this in later chapters. Some or all of this information may be kept in this section of the PCB. Memory management. In a virtual memory system, this section includes pointers to segments or pages of the process. I told you previously that the whole process image is divided into chunks. All chunks of the process are loaded in the hard disk area of virtual memory. If the process is not suspended, at least one chunk of its process image is copied in the main memory. In a virtual memory system that uses pages, each chunk has a fixed size and it is called a page. In a virtual memory system that uses segments, each chunk can have a different size than the others and it is called a segment. Execution can take place only of the segments or pages that are present in main memory. So when the processor generates an address that is not present in the page or segment currently in main memory, the operating system copies the page or segment in main memory to the hard disk and fetches the page or segment containing the generated address into the main memory. So process pages or segments are constantly being brought in and copied out of the RAM. This can only happen if we know the locations of all the pages or segments. So this section keeps their pointers. Resource ownership and utilization. Anything that a process may ask for is a resource. System resources include processor, memory, files, variables, messages, I/O devices, etc. This section contains IDs of the resources that have been granted to the process. Resource utilization history may also be maintained, but this will depend upon the operating system. So now I am able to present to you the complete picture of process description. Let us start with the process image, which contains four things: program, data, stack, and the PCB. If we blow the PCB up, there are three components. The first component is process identification, and within process identification, we see three more components: process ID, user ID, and parent ID. Coming back to the PCB, the second component is processor state information. And if you move into this component, you find three components here: user visible registers, control and status registers, and stack pointers. The last component of PCB is process control information. This contains six things: scheduling and state information, data structuring, inter-process communication, process privileges, memory management, resource ownership, and utilization. And this is how a process is presented and kept track of by the operating system. Let us look at another picture. This shows user processes in virtual memory. Here process images are contiguous, but it is not necessary that all pages of a process lie contiguously in virtual memory. Also, you can see that there is an area of memory that a process may share with another process, and shared variables can be kept here. Now that we have seen the structure of the process control block, it is important that we talk of the role of the process control block in an operating system. One thing that you must have realized by now is that it is the most important data structure in the operating system, because if something happens to the PCB, then your process is lost. The set of all PCBs in a system defines the state of the operating system. Every OS module reads and or writes the PCB. Problems with direct access of PCBs. If each OS module directly accesses all PCBs, a bug in a single OS routine can damage all PCBs in the system. A design change in the PCB can affect many OS modules. So if you change something in the PCB, you might have to write a lot of OS modules. You might have to rewrite the whole operating system. So what is the solution to this direct access problem of the PCB? The solution is make a PCB handler routine. All OS modules wanting to read or write PCBs must ask the PCB handler to do this on their behalf. Only a bug in the PCB handler will affect PCBs now. If the design of the PCB is changed, only the PCB handler has to be changed. But there is a catch. The system performance suffers as the PCB handler becomes a performance bottleneck. Now, some of you might not know what a performance bottleneck is. So let me explain. A performance bottleneck is a resource whose speed dictates the overall system's speed. Consider a very narrow lane leading to a 4-lane road, and you want to get to the wide road. You drive your car through the narrow lane where all cars are moving in single file. Even though the road can accommodate 4 files of cars, traffic on the road will be scarce because it is being fed by the narrow lane, which is slowing down all the drivers. No matter how wide you make the road, traffic will be as slow as the lane permits. So, the lane is a performance bottleneck. Saying that the PCB handler is a performance bottleneck means that the system will be only as fast as the PCB handler, no matter how much faster other OS modules are. Let's do a quick quiz. How many processes are ready? How many processes are blocked? Here, processes with the same state are arranged using a very well-known data structure. Can you name it? So finally, we are at the end of this lecture. What did we learn? First, we understood the process image. Then we talked about the process control block, and we did that in a lot of detail. And in this way, we understood the data structures that the operating system uses to manage processes. And finally, we realized the role of the PCB in an operating system. Finally, I leave you with a list of things to do. Read the book. Keep the Word file in which you were writing down the tasks for this lecture, because I will ask you to submit it via Google Classroom. Write your questions on a piece of paper and keep it in front of you during the online session relevant to this lecture. If you have suggestions relevant to content or quality of this lecture, email them to me. If you are feeling low, give yourself a pat because you have just finished the content of the first week of online classes. Only 9 more to go. Keep your chin up and smile. I'll see you soon. Allah Hafiz.